Welcome back. I'm Muggsy, and today I'm going to explain double and triple bonds. Before I talk about double and triple bonds, you should probably just understand covalent bonding in general. So if you don't know about that skill, check out my video on that. You're told that we breathe oxygen, right? But we all know that oxygen has 6 valence electrons, and so is unstable in its current state. 6 out of 8, no good. So you might have heard perhaps that what we actually breathe isn't pure elemental oxygen, but the molecular compound O2. I guess it's not a compound. The covalent molecule O2. 2 oxygens bonded together. So let's see what that looks like right now. We've got our 2 oxygens. I've got their single electrons facing each other. They form a bond. And now the bond counts as 2. This oxygen here has 2, 4, 6, 7 out of 8 valence electrons and is still unhappy. And so does this one over here, 7 out of 8 valence electrons, unhappy. So O2 doesn't appear to be a stable molecule. But there's another trick that atoms can use to become stable. So if there are no other elements around, just oxygens, what this oxygen can do is they shared these 2 single electrons. They can also share these 2 single electrons. And in doing so they form a double bond, which we write as basically like an equal sign. So if they share those electrons, we kind of remove them from the bottom. We've got our little equal sign there. Remember, each bond represents 2 electrons. So if this is 2 and this is 2, a double bond represents 4 total electrons. So this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 out of 8 valence electrons and is stable. And this one over here also has 2, 4, 6, 8 out of 8 valence electrons and is stable. So if you can't get it done with a single bond, you can use a double bond. Now you can't just go straight to a double bond because it requires more energy to form a double bond. So we only use double bonds if we can't get by with a single bond. It's kind of like if you were filling up a pitcher of water, the water wouldn't just go to the top of the pitcher before it filled up the bottom. It has to kind of follow gravity. It'll go to the place where the potential energy is least and then kind of work its way up from there. It's the same thing here. A double bond won't form if a single bond will take care of it and make the compound or molecule stable. There's one other thing to do here. And this is just a little extra, but I think it's pretty important to kind of show that you understand how electrons work. Remember, electrons have a negative charge, and negative charges repel. So if these electrons are all repelling each other, repelling, and these electrons, the electrons of the bond, are repelling these 2 paired electrons here, which are repelling these 2 paired electrons, which are repelling the bond, etc., then your electrons aren't going to be located like they are here. They're going to be located, let's start with the bond, which we always draw as an equal sign for a double bond there. And then we keep our paired electrons paired, but we want them basically equally spaced around that oxygen. So instead of having 1 at the top and 1 over here, we're going to have them kind of spaced equally around that oxygen, if that makes sense, so that each of these angles here are kind of about the same. So same thing here, kind of up here and maybe down here. Because all of these electrons are repelling each other, so you wouldn't have this big space here. In this bottom molecule, they're all kind of spaced evenly. All my little arrows are kind of roughly the same size. So moving those electrons just kind of shows we understand that the electrons are repelling themselves. Okay, so that's the oxygen that we breathe. That accounts for about, I think maybe about 20% of the stuff in the air that we breathe. What accounts for the rest of the stuff in the air we breathe? Well, most of it is nitrogen, N2. So let's see what that N2 compound looks like. So N2, the molecule, is 2 nitrogens bonded together. And we know that each nitrogen has 5 valence electrons. I always put the paired electrons kind of facing away because I know it's the unpaired electrons that are going to take place in the bond. So those are my 3 unpaired electrons kind of facing the other nitrogen, and same thing here. Okay, so let's form a nice single bond. And now both our nitrogens have 2, 4, 5, 6 out of 8 valence electrons. That's no good. So we're going to need a double bond. So let's share these bottom 2 electrons. Doo-doo-doo. And now both of our nitrogens have, the double bond counts as 4, 5, 6, 7 out of 8 valence electrons. Still no good. Fortunately, there's one more thing you can do, and that's a triple bond. So these electrons here, these unpaired electrons on top, can also bond. So if the nitrogens share those, we draw it as basically 3 parallel lines. 2 parallel lines for a double bond, 3 parallel lines for a triple bond. And of course, if a single bond counts as 2 and a double bond counts as 4, then a triple bond obviously counts as 6. So that counts as 6 plus 2 here for a total of 8 out of 8 valence electrons. And we have a stable nitrogen here and the same thing right there. So N2 is 2 nitrogens held together with a triple bond. And this accounts for about 78% of the stuff in the air we breathe. So every time you take a breath in, about 3/4 of it is this compound N2. And because it has this triple bond, and the more bonds you have, the stronger that connection, the harder it is to make, but the harder it is to break as well. And so this nitrogen is very, very strongly bound to this other nitrogen. So when you breathe it in, you're not going to break it apart. It's just going to exist as N2 in your body, and then you're going to breathe it out, and it'll still be N2. It's inert. It doesn't take place with any of the chemical reactions in your body. Oxygen does, because that double bond's easier to break. But N2, you breathe it in, you breathe it out. Okay, well, we're not quite done. There's other stuff in air as well. This has become a lesson about the atmosphere, I guess. And one of the things in the air that you're probably concerned with is CO2. So if we have CO2, what does that look like? Well, that's going to be a carbon and 2 oxygens. So let's go ahead and put that together. Our carbon has 4 valence electrons. It's usually the central atom because it can form 4 bonds, which is really cool. Makes it really involved in lots of different compounds. Here's our 2 oxygens. Okay, let's start bonding. So a single bond there to attach each carbon to each oxygen. Let's take inventory of what we have. This oxygen has 7 out of 8. It's unstable. This carbon has 2, 4, 5, 6 out of 8 valence electrons, also unstable. And this oxygen has 7 out of 8, just like the other one, and it's unstable. So let's start sharing electrons. If these 2 share, basically there's a double bond there. And if these 2 share, there's a double bond there. Let's rewrite it to look nicer. So whenever we have a bond, we just draw it as a line. So that double bond now just looks like an equal sign here. And same thing with this double bond. It's just going to look like an equal sign. And let's recount everything now. Double bond counts as 4, 5, 6, 7, 8. 8 out of 8, nice and stable. 4, 5, 6, 7, 8. 8 out of 8, nice and stable. 4, 4 for a total of 8. Nice and stable. So CO2 basically looks like this, a carbon connected by double bonds to 2 oxygens. Now, as we talked about earlier, we do want to do something with these electrons here to make the molecule look a little bit neater. And that is, if those electrons are repelling each other, then we're not going to have some at the top and some to the side and some on the bottom and some to the side. They're going to be like equally spaced around those oxygens. So let's do that. Let's keep them paired together, but space them out a little bit more equally. So we're going to have maybe 2 up here, 2 here. I think this kind of looks like a bow tie or something like that. And there you go. And let's make this look a little neater too. Let's make that bond a little straighter. CO2, a carbon connected by 2 double bonds to oxygens. And this is really trace in the atmosphere. I forget exactly how much, but it's much less than 1%. The other thing in the atmosphere is argon. Let's take a look at that argon and see if it's a double bond, or single bond, or a triple bond, or anything like that. So here's our argon. It's a noble gas. 8 out of 8 valence electrons. Is it going to be bonded to another argon over here? No, of course not. These argons have 8 out of 8 valence electrons. They're totally stable just the way they are, so they're not going to bond to other argons. They're going to stay by themselves and be totally happy. So argon, as it exists in our atmosphere, in the air around us, is just elemental argon. Noble gases are one of the few elements that exist in their pure elemental state because they're totally stable just the way they are. Kind of a little bit of a review there. Okay, so let's kind of review what we talked about with double and triple bonds. If you can get by with forming a single bond, do that. If you need to form a double bond, you can do that only if you couldn't do it with a single bond. And if you can't do it with a double bond, you can try a triple bond. What about if I had 2 carbons and nothing else? I could do a single bond, a double bond, a triple bond, and then a quadruple bond. Well, no. Quadruple bonds actually don't exist. And you can kind of see why. The orbitals where those electrons are placed are important. And it's a little bit advanced for an introductory chem course. But the reason we can have double and triple bonds is because these p orbitals line up. Whereas you'll notice these electrons out here are so far away from each other and they're angled away, so they have to do this weird, stretchy, swoopy thing to bond with each other. It wouldn't happen. The geometry of the molecule just doesn't make it possible. So you can't have quadruple bonds. That's a question I always get from students. The answer is no. You could, in order to make this carbon stable, put like a little hydrogen on the end there. Hydrogen has one. We can form a single bond there. And that's a perfectly stable compound, acetylene, sometimes called ethene. So yeah, no quadruple bonds. But you can remember, if you can do it with other elements, try and make it work that way first. Okay, let's do a few more examples. Let's go over a few examples of some covalent compounds and see if we can form them using single, double, or triple bonds as we need to. So let's start with S2H2. Typically, you'll notice these H2s or Cls are kind of at the end. These smaller atoms, or the ones that, let's say, can form fewer bonds, like hydrogen and chlorine can only form one bond. I think it's easier to always start with the more central atoms, which are typically in the front, but not always. So let's start with that S first. So an S sulfur has 6 valence electrons, right? So we can form a single bond to connect those 2 sulfurs. They now have 7 out of 8 valence electrons. They're not stable, but if we put a hydrogen there on each side, we've got 2 hydrogens to use. We can form single bonds. And now we have 2 out of 2 for our hydrogens. We have 8 out of 8 for our sulfurs. We have a nice, stable molecule. This one's happy all by itself. No need to mess around with double or triple bonds. If you can get it done with a single bond, do that first. You might have noticed that I have my hydrogens kind of in opposite directions. That's a little bit advanced for a basic chem course, but often that's something you want to do with your attached groups because, again, they want to be as far from each other as possible. A little advanced, don't worry about that. If you put your hydrogens both on the bottom or facing out, those would all be acceptable answers for my chem class. Okay, let's look at the next one. P2H2, let's start with our phosphoruses first. Phosphorus is in column 15, so it's got 5 valence electrons. And you'll notice I put my paired electrons kind of facing away because it's the unpaired electrons that are going to interact. Let's start by connecting them with a single bond. And then we've got 2 hydrogens, so we're probably going to want to stick a hydrogen on each of these. So let's do the same thing we did last time, a hydrogen here, single bond, single bond. Hydrogens both have 2 out of 2 valence electrons. They're stable. My phosphoruses have 2, 4, 5, 6, 7. 2, 4, 5, 6, 7 out of 8 valence electrons. They're not stable. They can use these electrons to become stable. So if they share those electrons, now this is kind of weird. This one's going to have to cross across like that. So let's maybe move where our hydrogen's placed, because they wouldn't want to do that in nature. So let's put our hydrogen down here. And now we can have a nice bond between those electrons. So let's form a double bond, sharing those electrons. And now our phosphoruses have 2, 4, 6, 8. 2, 4, 6, 8 electrons. They're stable. Hydrogens are stable. Everyone's happy. Again, I was kind of anal retentive about where my hydrogens are going. Little OCD. It doesn't matter for an introductory chem course. If you want them on opposite sides or wherever, that's fine. Okay, C2H2. Let's take a look at that one. Again, our carbons are probably going to be the central atom. They're first in the formula, so let's start with our carbons. 1, 2, 3, 4. 1, 2, 3, 4 valence electrons for a carbon. Let's bond them together. Now they have 5 out of 8 valence electrons. They still have a ways to go until they're stable. Let's tack on some hydrogens. So let's put one here, hydrogen, one here. Those hydrogens both have access to 2 out of 2. They're stable. These carbons now have 2, 4, 6 out of 8 valence electrons. They're unstable. So let's do another bond here. Okay, 2, 4, 6, 7 out of 8 valence electrons. They're unstable. Now remember, what I told you is we can't really have a bond like this. It just wouldn't work. The electrons aren't close enough to form a bond. They're so far away from each other. So I think what would really happen is we need to kind of remake our molecule here. And we need to stick those hydrogens over here. If we bond the hydrogen here, then we still have, our hydrogens are stable, but our carbons still need one more bond to be stable. But they now have these 2 electrons close enough so that their p orbitals can align and they can form this triple bond. So I would just rewrite this to look a little bit cleaner as 3 little parallel lines right there, and keep the hydrogens exactly as I wrote them last time, sticking straight out. And so this is what our compound would look like. C2Cl4. Let's take a look at that one. 2 carbons right in the middle. Each have 4 valence electrons. We've got 4 chlorines to stick on there, but let's start by just bonding those carbons together. And then let's start sticking chlorines on. So if we have a chlorine here, 1, 2, 3, 4, 5, 6, 7, we can have a single bond. That chlorine will be stable. Same thing here. Chlorine stable. Let's put another chlorine here. Stable. 7 valence electrons for our chlorine, and now that's stable as well. So we've used all 4 of our chlorines, and all 4 of our chlorines are perfectly stable with that one single bond. But our carbons now each have 3 single bonds for a total of 6 electrons, and an unpaired electron for a total of 7. So they're not happy. But if they were to share that unpaired electron there, they would be happy. They now have access to 4 bonds, a double bond and 2 singles. Each of those bonds are 2, so 2, 4, 6, 8, 2, 4, 6, 8. Carbons are stable. Now this is an ugly looking molecule. I like to redraw it as basically an equal sign. And then let's stick those chlorines on there. Make sure to account for every last little electron there. And in fact, this isn't quite complete yet. There's an issue with this, and it's the same issue we had earlier. If we look at the spacing, these chlorines are going to want to be basically equally spaced. And these are equal, but then there's a huge space between this chlorine and that double bond, just like there's a big space here between that chlorine and that double bond, and smaller spaces here and here. So let's just kind of draw it so everything's equally spaced, and it becomes this kind of like bow tie looking thing. So C, C, and then our chlorines go off at angles like that. Okay, so you end up with this kind of X-shaped or bow tie shaped molecule. Just to kind of make sure that all of our chlorines are equally spaced, because remember, these electrons, they're all negative, they're all going to be repelling each other. Okay, last one, HCN. Okay, for this one, I recommend just writing it out the way you see it. You could start with a carbon and then have an N. But what this is doing, HCN, is kind of telling, because often the H's are second. In this case, the H is first. It's telling you that this is actually what the molecule looks like. There's an H and a C and an N, and they're connected in that way. You don't need to know that, but that kind of helps you get started on this. Our carbon, like all carbons, have 4 valence electrons. Nitrogens have 5. I'm going to put the paired electrons on the far side. Hydrogen has 1. I'm going to put that 1 electron on the near side because all of these are going to interact. Let's just bond everything up with single bonds. Single bond. Okay, let's take count of what we got. Hydrogen, 2 out of 2 valence electrons. Totally stable. Carbon, 2, 4, 5, 6 out of 8. Not too happy. Nitrogen, 2, 4, 5, 6 out of 8. Not too happy. Okay, let's make this a double bond. Now we've got 2, 4, 6, 7, 2, 4, 6, 7 out of 8. Closer, but still no cigar. Let's try this bottom one, connect those. Now we've got 2, 4, 6, 8 out of 8 for this carbon. Totally stable. And 2, 4, 6, 8 out of 8 for this nitrogen. Totally stable. Let's redraw it to look nice. Hydrogen straight out from a carbon with a nice 3 parallel lines connecting it to a nitrogen, and nitrogen with 2 paired electrons facing away from that carbon. Because remember, these are negative, these bonds are negative. They're going to be as far away from each other as possible, so that's perfect. Same thing here, going to be as far away from each other as possible. That's perfect. So that's what this looks like. This is actually hydrogen cyanide. You may have heard about it. I think it's what Hitler took to end his life. It's a poisonous substance. It's found in apple seeds, all that kind of stuff. Whatever. Double and triple bonds, it's kind of fun putting these molecules together. I really enjoy drawing Lewis structures. I hope you do too. Remember, the big rule here is don't use a double if you can use a single, and don't use a triple if you can use a double. It takes less energy to make a single than to make a double, and it takes less energy to make a double than to make a triple. And in nature, everything's going to do what takes the least amount of energy. A boulder's never going to start rolling up a hill on its own unless you push it. It's always going to choose to roll down because that takes less energy. Okay, yeah, I wish you well practicing this. I hope this made a lot of sense. I think it did. I'll see you next time. Take care.